This is another section in the textbook that I feel is slightly misnamed. It's called the existence and uniqueness theorem, but I really feel like it should be called the existence and uniqueness theorem, Picard's method. It's really this technique or this method of finding a solution to a differential equation, which is different from things we've done so far this quarter. It's really this technique that's highlighted in this section. The existence and uniqueness theorem really is, while it's addressed and the qualifications that need to be met are important, the focus really is on the technique. So I'm going to leave it called what it's actually called, but know going forward that the title is, I think, misleading. So let's get rid of this, and I'll move this title out of the way, and then we'll take a look at, very briefly, we'll take a look at the existence and uniqueness theorem with a couple of adjustments, we'll call them. The first one is that when we're given a differential equation, like, for example, y prime equals f of xy with a set of initial conditions like y of 0, actually I'm going to use a different number here, y of 3 equals 2, we can determine whether this equation has a solution, and if it does, whether that solution is unique. We've done this before. We talked about it in section 2.4. I'll address it briefly here with a particular focus in mind, and that is that the 3, 2, the point 3, 2 is the place where the initial conditions are set, right? That is the place around which we're looking for a solution for this differential equation, a particular solution. For convenience, if we're given a set of initial conditions, like the ones that we have here, this point is at 3, 2. So let's go ahead and plot that in there. And let's say, for example, that I've got an equation that tells me, I'm making this one up, and I don't have an actual equation here, but let's say that I have a differential equation that tells me something about the slope field around that point, right? Around at y equals 2, the slopes are positive and fairly large. Above that, they're even larger. Below that, they're smaller, but they're still positive. Well, if I just grab that whole slope field and move it so that my my initial conditions are 0, 0, but the slope field moves with it, then I'm solving the same problem. I'm solving the same differential equation from a different perspective. So now what I'm really doing is I'm solving the differential equation. I'm going to call this one y sub 1 equals f of x plus 2, comma, y plus 3. But other than that, it's the same problem. My initial conditions are now y of 0 equals 0. Right, so I'm working from the point 0, 0. Other than the position from which I've started, everything's the same, including the slope field, because I moved the slope field with, instead of starting at 3, 2, I started at 0, 0. But everything I come to know about this equation is the same as it would have been in that other position. What we say, this is a lovely turn of phrase, I think, we say that there is no loss of generality. And what that means is that if I move things around so that I'm working with a more convenient location or a more convenient function, if I have done that in such a way that it doesn't change the problem, then we get the easier problem to solve, or the easier problem to look at, or the easier starting place, without losing the generality of the proof that we're going to do, right? The proof has to be general because it needs to account for every possible case. That's what proofs do, right? If I said 3 squared plus 4 squared equals 5 squared, there I've proved the Pythagorean theorem. I'll say Pythagorean theorem, right? I haven't. I have shown it to be true for one particular instance. I have not shown that a squared plus b squared equals c squared, a and b, c in real numbers are real numbers. And well, my pen has just started really fighting with me. It just won't work sometimes. A, b, and c are real numbers, and are the sides and hypotenuse of a right triangle. These conditions all have to be met first, but once they are, then this statement is true. But it's true regardless of what a, b, and c are, not for a specific case. So we need our proofs to be general, or we haven't really built a very effective tool, right? So we need our proofs to be general, but when we do something like this, move things around so that they're more convenient, as long as we have considered the possibility that change might have affected things. If it doesn't, then we can say, without loss of generality. I love that phrase. If you write many proofs, you'll start to hear that a little bit. Without loss of generality, just do a convenient change of variables so that your initial conditions are 0, 0. And then once you've established that, we're going to look now at something called Picard's method that lets us go about solving, either solving a differential equation if we don't know how, or we don't have the tools, or if it can't be solved using the previous manipulation techniques. It's kind of hard to describe, so I think I'm just going to dive in here. I'm also going to erase the second line here because this, where's my pointer? This is a little messy, but we've just demonstrated that we can assume that the starting point is 0, that the initial conditions are 0, 0, and if they're not, we can change things so that they are, right? I might say that this is now u, comma, v, for example. So I can change things around so that they're convenient. So I'm going to go ahead and erase this line, and I'm going to change my initial conditions to 0, 0. Y of 0 equals 0. Actually, I think I'm going to do something even more general than that. I'm going to say that your initial conditions are y of x naught equals y naught. So when I plug in a specific x value into my function y, once I know what it is, this is y prime, but once I know what y is, if I plug x naught into that function, it's going to spit out y naught. Okay, so I have now a very generic differential equation and a set of initial conditions. This is an initial value problem. I'm going to make another change here, and the reason may not be obvious initially, but I'll explain why as we go along. I'm going to change this from x comma y to t comma y. Remember we said that basically, there we go, t or x, it doesn't really matter which one you use, but given how I'm going to use the t or x or t in this particular method, I'm going to need a dummy variable. And rather than use a variable of x with a dummy variable u, I guess I could do it that way, or w, I've just chosen, in part because it's how your textbook does it, I've chosen to use the variable t with the dummy variable s. So once we get to that point, I'll explain things again, but that's why I'm changing this. The next thing I'm going to do is rewrite this into the form dy dt equals f of t comma y. And then I'm going to, I can't actually integrate because I don't have a function. I don't know what the function is to integrate. But let's say that I'm going to integrate with respect to t. On the left-hand side, I can do this, which leaves me with the integral of dy. Well, that's just y. So I can rewrite this as y equals the integral of the function f of ty dt. And that's our answer, right? I mean, hasn't the whole point of this been to find out the function y that solves this differential equation? The function y whose derivative is this other function of t and y. The problem is that this looks like it's solved for y, but there's a y in here as well. There may not be. I mean, this may be a constant or maybe even a 1, but in most cases it's going to be the variable y. And so we haven't really solved it for y. We have found a way to represent y as an integral. And that's what we're going to be working with in Picard's method. What we're going to do is we're going to take an initial guess. We're going to say y equals some function All right, we'll define what that is in just a minute. I'm going to take that function, I'm going to replace y with it here. I'm going to do this integration, and ideally what it will spit out is the same function as I write this, the function that I plugged in here with as part of this function. Once it's integrated, will just be that function. There's a very good possibility that it won't be, and so we need a slightly different way to annotate what we've got here. I'm going to start by renaming this y just capital Y. And I'm actually going to, no, I think I'll come back to that. So that's capital Y. It's just a notationally convenient way to represent the same thing. It's going to end up being a specific function in a minute. But then what I'm going to do is I'm going to take that function and I'm going to plug it in here. So this becomes, give myself a bit more space here, y, which is the function that I have described above, my sum function. My pen has stopped working again. So I have some function I'm going to plug in there, and it's the function that I get from here. We'll talk about that one in a minute. And then I'm going to integrate it. The problem is I'm going to integrate it from 0 to t, and that means that I've got a kind of a conflict of variables here. So the other thing that I'm going to do, and this is why I changed this to t so I could use s instead of x, in which case I would have to have used u or something. I'm going to change this to an s. I'm going to change the t's to the dummy variable s. And then it's also important to note that having changed that, isn't quite enough space either, having changed that this function y is also a function of s, right? And that's what's going to go in here. And I'm also going to make the observation that once I do this integration, I may or may not have the same answer as the function I plugged in. Because there's a fairly slim chance of that, I'm going to assume that I get a different function out. And so I'm going to call that function capital Y also, but I'm going to call my initial function y naught, and I'm going to call my new function y1. Okay, so now actually I have, I'm not sure how much of this I can move around. Well, it took me a minute, but I got it. So I'm going to move this one in here. I now have a y sub 0, a y naught, a zeroth function, if you will. And then I have a first function. So once I've decided my first function, the one I start with, function 0, I'll plug it in, do some work, and it'll spit out a new function. And then if that still doesn't match, I'll do it again. And that could give me a potentially new function again. I will have the integral from 0 to t of the function s with my, not with y0, that was this function here. Now I'm going to use this function, y1 of s. Plug that in, do the integration, and see what comes out. And depending on the situation, I may have to do this a large number of times. And so one of the things that it will be nice to take away from this exercise is a way to annotate or a way to record what you're doing in a very concise way. So I'm going to start by writing this as an nth integral. My nth answer here is just going to be the integral from 0 to t of the function f of s comma y sub n minus 1 of s ds, because each time I took the function I got from the previous answer. So the function that when I'm doing this for the nth time, I need to plug in the function I got the time before that, right? 1 less than n. You might be forgiven for wondering why I'm bothering with a definite integral in the first place. Well, remember that an indefinite integral is going to produce a function, which is what we're after, but a definite integral is going to produce a number. And what we know is something about the specific case, the specific point that the solution to this differential equation goes through, right? And these values are numbers, right? Y naught is a number. And so I'm trying to force this problem to not only to give me the solution in the form of a function, but better still, to give me the solution in the form of a number. And so once we decide what our first function is going to be, when we do the integration, if we do a definite integral, then it'll spit out a number. Well, actually, it does spit out a function in t, right? But if our initial conditions are 0, 0, then if you plug in t equals 0, you integrate from 0 to 0, you get 0. And so we get input of 0 and an output of 0. It satisfies those initial conditions. So that's why we're doing a definite integral. So let's do an example. Let's say we have the differential equation y prime equals y minus 1. Now, and I'm going to go with y of 0 equals 0. Okay, now we can solve this equation. This is just a separable differential equation. So I'm going to go ahead and do that very quickly, not because this is the approach we're going to take in this video or in this lesson, but once we do use the approach that is the point of this video, we can look back to this solution that we found here and convince ourselves that the new technique actually works. So let's very quickly, this is a separable equation, let's just very quickly work this out. This is dy over y minus 1 equals dt. When I integrate both sides, I get ln of y minus 1 equals t plus c. Exponentiating both sides gives me y minus 1 equals k e to the t. So y equals 1 plus k e to the t. And then if I plug in the initial conditions 0, 0, I get 0 equals 1 plus k e to the 0. I'll change the color of my pen for that. I get a 0 here and a 0 here. And that gives me 0 equals 1 plus k. So k equals negative 1. And my final answer here would be y equals 1 minus e to the t. That is the solution to this initial value problem. But as I mentioned a minute ago, that's not really the point. So let's go back and use Picard's method to try to get to the same place with this. To do that, we need to make our first guess at a function, and I'm going to make that 0. And that is because the output is 0 for some input, and here it is. The output that I want is 0 for some input, and so I'm going to stick with that output and see what happens. That's my first function. That's my 0th function. My first function, my first iteration, is going to be y1 of s. That's going to be equal to the integral from 0 to t of the function. Let's see, when I did it over here, I'm trying to point out where I'm going with this. I'm using the function f of ty, which becomes the function of s and y. And that comes from this place right here. That's my y prime. So I'm using this function right here. So my y prime, my f of t and y, or my f of s and y, is that function right there. So that's what's going to go in here. And I will just write it that way for now so that we can see what's happening. That's the function that's going to go in there, and I'm going to integrate with respect to s. However, I know what that function is. See, this is a function with variables s and y of s. And what we're going to do is, for our first iteration, we're on this step right here, we're going to replace all my y of s's with this sum function that we selected. And the sum function is 0 in this case. It will be 0 in many cases. So I'm going to replace my y with 0. And that means that I'm just integrating -1 with respect to s. So I have y sub 1 of s is equal to -1 times s from 0 to t, which is -t minus 0, and that is my y sub 1. And then to get the next one, y sub 2, we just integrate from 0 to t, y minus 1 ds. However, we replace that y with -t, except because we're integrating with respect to t, we want to use the dummy variable -s, or s, so we have this. Then with respect to s, when I integrate with respect to s, I think I want to rewrite this, first of all, as negative the integral from 0 to t of s plus 1. And then integrating with respect to s, I get negative s squared over 2, put that in parentheses, plus s from 0 to t, which is negative t squared over 2 plus t minus 0. And that is my y2. My y3 will be the integral from 0 to t of that function, negative t squared over 2 plus t minus 1, right? This is my y. I'm integrating y minus 1. I'm just replacing y with that new function. And then I'm also replacing that variable with the dummy variable s to do the integration. And that gives me, I won't work that one out here, but I'll tell you the answer. When I do that integration, I get negative t cubed over 6 plus t squared over 2 minus t. And if I do the same thing for y4, I'm just going to do one more here. y4 of s will be the integral from 0 to t of this function here minus 1. That function there with t replaced by s is going to be negative s cubed over 6 plus s squared over 2 minus t minus 1 ds. I want to integrate that. I'm going to get, for the first term, negative 1/6 of s to the 4th over 4. And the over 6 and over 4 gives me 24. And of course, we're switching back and forth between here, s and t here, and I keep forgetting to make that switch, so let me correct that. The next term is positive, and I get 1/2 of s cubed over 3, so that's going to be t cubed over 6. I think it's very interesting to note that that term also appears in the previous version. The next term, minus t, gives me minus t squared over 2, and that term appears in the previous version. And then the minus 1 gives me minus t, and that appears in the previous version. And then, of course, it's minus the same thing integrated, the same thing evaluated at 0, right? That gives me, that just gives me 0. So one observation I'd like to make here is that this is the 4th iteration. This is the the best approximation to a solution we have to this differential equation so far, okay? The one before that was good, but not as good as this one. The other observation I'd like to make is that in my zeroth answer is 0. My first answer, my y sub 1, is negative t, right? There it is right there. Let me outline these. That was my first answer, my first equation. Right, so I've got outlined, got these all outlined now. There we go. My first answer was minus t. I forgot to subtract that t there. I forgot to distribute that t there. So that should be a negative as well. It should be, oops, not there. Erased the wrong thing. That one is positive, and this one is minus t. So I have a minus t here, I have a minus t here at the end, I have a minus t here at the end, right? And then the next one adds the negative t squared over 2 to the front of that. Oh, I've forgotten. Because I had a plus there, it's propagated all the way through. So I've got errors all the way through here. Hang on a second. Okay, I think I fixed all of those now. So I have minus t squared over 2 in this answer, in this answer, and in this answer. The next thing that gets added is this is negative t cubed over 6, and that's also present here. And then the one after this, y sub 4, would have all of these plus another term, right, at the beginning. So I think that's an interesting observation, and more interesting still, I think, is the fact that we can use this pattern to write the nth solution to this iterative process. We're going to say that y sub n of s equals, I'm not sure I like where that is, but I've run out of room, typically. I wonder if I should write this in a different place. I think I will. I'm going to erase the left-hand side of the screen, and I'm going to use that space instead. So that's better. All right, so what I want to do here is say that the nth iteration of this is going to be the sum of several terms. I don't know if you remember from some of your previous work in earlier calculus classes, that means the summation of. And now what I need to do is figure out how to write a single term that identifies what's getting added each time here. I get a new exponent and I get a new denominator. I could write this last one down here as over 1, so let me do that. And I could have a power of 1. So at first it looks like the denominator is going to match the power, but it doesn't, right? It stops happening here. How to explain this without going back and reworking all of these? When I got this term here in y sub 3, I got it by integrating negative s squared over 2, and I did that by taking the negative 1/2 out front, so I had a 1/2 here, and then my integrating s squared gave me s cubed over 3, so I had a 1/2 and a 1/3, and that's what gave me the 6th. Here, I integrated this term. I took the 1/6 out front, so I had a 1/6, and then I had s cubed over 4. So I already had a 1/3, and then I multiplied it by a 1/6, then I multiplied it by a 1/3, or a 1/6 multiplied by 1/4, and that's what gave me the 24 here. So each one of these terms is the number of the iteration I'm on times the old denominator, right? Or it's the number of the exponent times the old denominator. Kind of depends on how you look at it. The exponent's going up by 1, and the denominator is going up by being multiplied. The number of the exponent, or the number of the iteration that we're on, being multiplied by the new exponent. So let's see, how could we write this? Well, the top is easy. We can just say it's t. I gotta get the right pen here. T to some power I. And the bottom, first of all, let me note that these are all negative. The bottom is some number times the previous number times the previous number times the previous number. And for that, we need something called factorial notation, which some of you may have met and others of you may not have met. So here's a quick introduction to factorial notation. 3 factorial just means 3 times 2 times 1, and that's where you stop. 7 factorial means 7 times 6 times 5, all the way down to 1, and that's where you stop. 19 factorial, don't worry, I'm not going to write it all out because who's got time for that, right? Times, and so on, all the way down to 3 times 2 times 1. Your calculator can probably do factorial computations. Most calculators can do that, but that's not the point. The point is we're trying to find a way to write not the first or second or third or fourth answer we get, but the nth answer. And so we don't know how many times we're going to have to do this. We need to find a way to write this number as a product of numbers related to the exponent. So here I have 1, which is the first number. I guess I could start, I could add a few to my explanation here. This is just 2 times 1, and this is just 1, because we always stop with 1. That's the lowest number. You start with this number, 19 times, and you go on. You stop at 1. You start with this number, well, that's 1, and you also stop with 1. So 1 factorial is just 1. 2 factorial is 2. 3 factorial is 3 times 2 times 1, that's 6. I'll stick another one in here. 4 times 3 times 2 times 1, that's 24. Okay, so 24 can be written as 4 factorial. The one before it, 6, is 3 factorial. The one before that is 2 factorial. I've moved those down out of the way now because I want to write this denominator as something factorial. And the thing I have to ask myself is, what is the number that's getting multiplied from that number down to 1? And we decided that this last one we had here was 4 factorial, right? That was what gave us 24. And 4 in that case, the 4 factorial, the 4 there matches the 4 in the exponent. The 6 here is 3 factorial. The 3 in the factorial matches the 3 in the exponent. So what I'm going to have here is I factorial. So the I is the thing that's changing. What I'm doing here is representing a sum of lots of different terms. Maybe I should put parentheses around this whole thing. We could move this negative sign out front because of the properties of sigma notation, the properties of sums. We could factor that out and move it out front here. I'm going to leave it where it is at the moment just because it's obvious that all of my terms are negative. What I need to do now, this summation notation is incomplete as it is, because what this argument here is telling me is to take a t and raise it to some power and then use that same number here in the denominator and create the factorial. But it doesn't tell me what I is. And I is the index. This is just conventional notation. Somebody came up with this once upon a time and we've kind of used it ever since. But this is how we use it. We say that I is some number that starts here and ends here. And in this case, we want our, I'm going back to my my y sub 4 down here. We want our I to start at 1, right? So I'm just going to put in I equals 1. That's our starting place for I. And then we have to ask ourselves, well, how far do we want to go with this? I'm trying to get my pen to work. Where do we want I to end? How long do we want to do this? We kind of want to do it indefinitely because in theory, the more iterations of this process you go through, the better your answer is going to be. At some point, hopefully, maybe in some cases, you'll keep getting the same function out over and over again, and so you can stop. That's your answer. But not in all cases. And so we want to take into consideration the fact that we may have to do this somewhat indefinitely. So let's say we're going to go to n, and we don't necessarily know what n is. N is some number we're going to stop at, right? we could, in fact, now even take the limit of this summation, and I will talk about that in just a second. First, I'm going to erase my mini lesson on factorials. Okay, so what is the limit of y sub n of s? It's the limit of this summation that we've identified, negative t to the power of I over I factorial. And we want to take the limit of this thing. We want to ideally do this for an infinite number of iterations, right? If we've decided that the number of iterations, the larger the number of iterations, the better the answer is going to be, then let's just do it forever. Well, that's literally impossible, but in terms of limits, it's not impossible. So let's say we're going to take the limit of this thing as as n goes to infinity. So we're going to start at 1, but then we're going to do t to the 2 over 2 factorial, add that to t to the 3 over 3 factorial, subtract it really, t to the 4 over 4 factorial, and so on forever, right? So on until I gets to n, but n is going to infinity. Now, the next step is really kind of cool. Some of you may have met series expansions before, but I suspect many of you haven't. So I'm going to do just a little bit of manipulation here. I'm going to say that this is equal, first of all, to, I'm going to take 2 steps at once here. This subtraction problem, this minus, this negative in front here, that can come out in front of the sum, but then because of the properties of limits, it can also come out in front of the limit. So that's going to be equal to negative the limit as n goes to infinity of the sum from I equals 1 to n of t to the I over I factorial. And then I know something about this piece right here that some of you may know, but others of you don't or won't. And that is that if it was, instead of being the sum from 1 to n, if it was the sum from 0 to n, I'd be able to say something about it. So I'm going to first rewrite it as the sum as I goes from 0 to n. And then what I've done essentially here is add a term. That's a very big I. Let's try that again. Okay, I've added a term. I've said, go back to the bottom right-hand side of the screen. I've said, start not down here, but one term before that, where t equals 0. And that's, where I equals 0. And that's going to be, let's see, t to the I over I factorial when I equals 0 would be t to the 0 over 1 factorial. Well, anything to the 0 power is 1, and 1 factorial means start multiplying at 1 and end multiplying at 1, so you get just 1. So basically, this sum here is bigger than this sum here by 1. So these two expressions, this limit here and this limit here, are no longer equal. If I want to make them equal, I need to make some other adjustment to this to make sure that it's still equal to that one. So what I'm going to do is I'm going to, first I'll partition this off in parentheses, and then I'll partition this one off in parentheses. And what I've been saying is that this expression is bigger than this expression by 1. So if I want this one to be the same as this one, what's in the parentheses here to be the same as what's in the parentheses here, I need to subtract 1 from that sum. Now they're the same. Why would I do that? Well, hang on a second. Let me erase. I'm going to erase down here now. I'm going to distribute next. I'll distribute my negative sign that's up front here, across here. That gives me, and I'll switch the order of the terms. I have negative, negative 1 minus the limit as n goes to infinity of the sum. Oh, I can't draw a summation notation for some reason today. There we go. I equals 0 this time to n of t to the power of I over I factorial. And I know, and as I've said a couple of times, some of you maybe know, that this limit turns out to be, if you've had any sequences in series or series expansion work, that turns out to be e to the x, or e to the t in this case. So I get 1 minus e to the t. Now, I promise you I'm not making that up. It's hard to believe, but that is the solution that we came up with before, right? So if I do this Picard's method for 4 terms, I get this polynomial. And if I could do that an infinite number of times, then I would get the exact solution, right? The exact particular solution of the differential equation I started with. Now that I've done all of that, I want to say something else. I don't really expect you to be able to do this. This is a really nice, neat notation, and it's very handy to be able to manipulate mathematically in this way. The more math you take, the more likely you are to see this kind of notation. I kind of wanted to throw it in there because it's really nifty. And I wanted you to have some exposure to it. And I may use it further into the quarter. We'll see. But as you write answers to questions in assignments and on quizzes and exams, this kind of notation is fine. I probably, in fact, will say specifically, use Picard's method through iteration 4. Or, let me see, I've got a problem right here. I can preview it. It'll tell me. Given the differential equation, y prime equals, and there's a differential equation, find the corresponding Picard iterates, y sub 1 and y sub 2. So your answers to that question in an online environment would be negative t, and this one here, negative t squared over 2 minus t. In other instances, I might ask you to give me 3 or 4 iterations. But the answer can be in this form. It doesn't have to be in this form. That said, I really like this, and I have kind of used it in this particular instance to indicate or to demonstrate the answer that we get using Picard's iteration method of successive iterations does give us the same solution as we got in just using separation of variables. Now, this video has become rather long again, so I'm tempted to do another example, but I think I'll do it in another video. So let's call it good for this one, and I will see you in the next one. If you feel like you have enough, then you don't necessarily need to watch the next video, but we'll just do one more example there so that we can kind of draw a line under this.